In this module, we will talk about the steady-state approximation. With the steady-state approximation, more precisely quasi-steady-state approximation, we assume that in a complex reaction mechanism, the concentration of intermediate species remains low and constant throughout the reaction process. More specifically, the reaction first goes through an induction period when the concentrations of intermediates increase from zero. Afterwards, the reaction enters a phase where the rates of change of these intermediates concentrations become negligibly small. These rates are not exactly zero, but are sufficiently small for the most of the reaction. This figure visualizes the steady-state approximation. It illustrates that during the majority of the reaction's course, the concentrations of intermediates remain small and undergo minimal changes. Despite the dynamic nature of chemical reactions, where the reactants are continuously converted into products, the intermediates' concentrations can be considered almost constant. This leads to a key aspect of the steady-state approximation. The time derivative of the concentrations of intermediates is approximated as zero. The steady-state approximation simplifies how we understand complex chemical reactions. By assuming that the amount of intermediates doesn't change much during the reaction, we don't have to track every small change in their concentrations. This makes it easier to focus on the overall reaction process. The steady-state approximation works especially well when the rate constant of the intermediates decay is large. In this case, even small amounts of intermediate lead to large rates of its consumption, not letting the significant amount of the intermediate to accumulate. Let's consider an example to understand how to apply the steady-state approximation in a sequential first-order mechanism that we had already considered. With this approximation, we set the rate of change of concentration of intermediate B dB by dt to 0. This leads us to the equation K1 times the concentration of A minus K2 times the concentration of B equals 0. From this equation, we can deduce that the concentration of intermediate B equals K1 over K2 times the concentration of A. This result is a direct consequence of the steady-state approximation, which assumes that the concentration of the intermediate is relatively low compared to that of the reactants. This condition is met when the rate constant K1 is much smaller than K2. As a result, even though the concentration of B is linked to the change in concentration of A, the absolute changes of its amount are very low, especially when K1 is significantly smaller than K2. This fulfills the two key requirements of the steady-state approximation: the low concentration of the intermediate and its negligible change over time. When we substitute the value of concentration of B into the equation for the rate of product formation, we arrive at a simplified expression. The rate of formation of product C dC by dt is equal to K1 times concentration of A. This implies that the rate at which C is formed is identical to the rate at which A is consumed, and both these processes are controlled by the rate constant K1. Essentially, this means that there is a steady flow of matter from A to B to C without any significant accumulation of B. The solution of this equation is particularly insightful. It demonstrates that the concentration of C over time is governed by the same expression we have obtained for this reaction mechanism under the condition where K1 is much smaller than K2, but achieved in a far more straightforward manner. This highlights the utility of the steady-state approximation in simplifying the analysis of complex reaction mechanisms. To illustrate the effectiveness of the steady-state approximation, let's consider this figure. Here we see a comparison between the exact results for the concentrations in a sequential reaction, represented by solid lines, and the concentrations obtained using the steady-state approximation, shown as dotted lines. Specifically for the case where K2 equals 20 times K1. This comparison effectively demonstrates how the rate loss derived using the steady-state approximation can closely mirror the actual behavior of the system, even when the rate constants are not drastically different in magnitude.